So in this video, I want to put some remarks on Markov decision processes in dynamic programming. So what did we learn in the last two lectures? So I really like to make things clear a little bit with videos already. So we introduced the basic reinforcement learning paradigm. That means that all goals can be described by the maximization of expected cumulative reward. And this is hopefully also something that you have seen in the previous MDPs that there might also be, depending on how you configure your MDP and how your state space and all the transition rewards are actually aligned, that you might either sacrifice or take risk for your agent and to estimate a value function, then finally and to extract your policy. We also learned about the formal description of Markov decision processes, where you have the agent environment interface, where we just said that there's an agent, there's an environment, and we at each time step the agent is at a certain state st. It performs a certain action AT and it receives a reward RT. And at each state, the environment receives an action AT, it provides a reward, and it moves internally from a state ST to a state ST plus 1. And we increment a time, a discrete time counter. And we also saw examples where we had problems or MDPs where we have some terminal states, so we have episodic reinforcement learning problems, or we have also seen examples for continual reinforcement learning problems like balancing a carport or something like this. We ended the MDP discussion on formalizing a little bit what we want to maximize in the end. So what we came up with was the expected long-term value of a state S, where we introduced state actions and probability transition functions, the reward function, and also our discount factor. And then we could say that, okay, the expected long-term reward of a state S is simply all the discounted sum of reward that we can expect if we start at the state S. And this is actually which led us to the thing that we want to actually maximize. So we want to maximize the expected return G. The thing is, if we want to maximize this thing, the only way of actually doing this, because actually the MDP is something fixed, so states and actions are fixed, probability and dynamics are fixed. The only thing is that we can change is that we can change how we select actions. And this is something that we do over a policy. We usually represent a policy using the term pi, and this represents our controller. Pi determines the behavior of the agent, so depending on the state S, it gives us an action A that we should take in order to maximize something. And this is actually the mapping that we want to optimize. So this is our mathematical formulation or function that we want to optimize. So this holds exactly for both, for deterministic as well as stochastic policies. So the one defining a deterministic function, the other one defining a probability distribution. Although we focused on deterministic policies in the previous videos. And actually, the new goal is actually to find a policy that maximizes the expected return, because this is actually the thing that we can actually maximize. We did that in the previous lecture by means of dynamic programming, and we introduced the principle of optimality, where it says that we can, if the problem is sufficiently structured, we can say we are optimal if we take the first optimal decision and then we keep on being optimal. And this is basically the main workhorse behind dynamic programming in general, but also how value iteration and policy iterations are being used to solve Markov decision processes. Yes, so actually we have seen that through these two algorithms and using dynamic programming, we were able to find optimal controllers for given MDPs. Both of these methods are actually guaranteed to find optimal solutions for both Q and V in polynomial time. I also showed you a little bit the intuition behind the proof, how this actually works, or why actually the policy is actually an improvement over the previous policy. And Yes, and while we have seen in value iteration where we directly worked on the state space, so we actually calculated the values of the states, in policy iteration we had an explicit representation of a policy that we evaluated, then we updated, and evaluated, and we updated. In both of these algorithms we actually performed sweeps through the entire state space in the inner loop, and then we also had outer loops for convergence monitoring, and both of them implement Bellman equation updates. Value iteration works on the Bellman optimality equation, and policy evaluation worked on the Bellman expectation equation. And both of these algorithms actually use bootstrapping. Bootstrapping is something that that I did not mention so far. In bootstrapping just means that we bootstrap state values based on previous state values. So we actually update our information on the environment. And what we usually also see in reinforcement learning is a notion like this over so-called backup diagrams. So what you see here is you see an initial state ST, and so this is actually all the rollouts that we can get starting from a state ST. So different actions give us rewards, and we end up in next states, and we go on through this down this tree. There is also terminal states. And bootstrapping just means that in order to update our estimation of ST, we refrain to the values that we have from ST+1 and the rewards for one step look aheads that we get until here. So this means bootstrapping. So we actually bootstrap the values from the back to the beginning, and we do this all over again, and then at some point we converge. This is what we have seen in policy evaluation as well as in value iteration. So now one final remark on that. The question is, so if you look in reinforcement learning literature, you usually see other algorithms than that, but are these simple algorithms usable? So as a hint, we are not done yet with the reinforcement learning class, so there's a lot that we will discuss after that, but also we see applications of these algorithms in practice. There was also, for instance, a nice paper called LightLearn from 2019, where you actually optimize a personalized lightning control with value iteration. And how do you do this? So you actually can define your state space and your action space. And what you actually did is, in an indoor environment, you learn a transition model. So at which periods and times are indoor lighting levels on and switched on and off. You learn a transition model for that, and then you can actually roll out everything and run value iteration on that. And this actually turns out to be then giving you a controller that it's really nicely fitting to the actual occupants of the environment. So it really like optimizes lightning control towards the occupants of the building. Another nice application is the large-scale order dispatch in ride-hailing platforms, something like from Uber or Lyft, where always the question is that you have many people on the one side that need a ride or need a scooter, and on the other side you have scooters or drivers, and you need to match them at some point. And you want to match them, of course, that they can quickly go from A to B and have low waiting times. But on the other hand, you want to also like you always want shared rides and things like this. So you have like you have to make a trade-off between all these variables. And what you would classically do is you would like separate your monitoring frame into short time frames, like 1 or 2 seconds, and then you have all these demands and all these offerings, and then you would run a combinatorial optimization on that. This is like what you can do. It's no problem to do this, but you can also do better. And the idea in this paper was actually to design such a dispatch operator that does a long horizon planning over 2 or 3 hours, and planning on how to actually assign drivers to demanding people, and yeah, so actually do a long-term planning on how to assign things. So not having a short-term horizon to actually do things, but also through experience, learn a value function on how can you perform, and then in order to with this value function in your back of your head, you decide on the current time what to do. There's also a nice video on that. I think you find it if you go on this link. So actually you can also define an MDP. You say, okay, the reward is actually the price, because if you already use such platforms, if you like share a ride, then you have to pay less. On the other side, for the drivers, it's better to have many shared riders, because actually in total they get more reward. However, they do not get a reward if they have to drive all over the city to actually reach you without taking anyone with them. And what you want to have is, in this example, you want to maximize the overall gross volume for the entire platform. And yeah, so actually you have a learned value function as an input This learned value function is something that you can estimate from historical data. And then you use this value function and the current situation to actually find a better mapping between all the drivers and all the orders. And this is something that you really can achieve in real time. And just let the video go until it terminates. Yeah, so actually they also used real data on that and improved actually the gross margin by up to 5%. Yeah, so actually you can use such algorithms in practice. Of course, they also have limitations, and about these limitations we will talk in the next videos, where we also provide to you also some solutions to that. So here are some references that you can look into if you're more interested in that. And yes.